Alright, let's go. Number 12. The line you cannot feel. In 1932, Georges Lemaitre was not thinking about black holes. He was a Belgian priest and cosmologist working on expanding universe models, and he had run into a piece of bookkeeping that annoyed him. Carl Schwarzschild's 1916 solution to Einstein's equations blew up at a specific radius. Everyone assumed that meant something was physically there. Lemaitre wanted to clean up the mathematics before publishing his Cosmology. The prediction was straightforward. At the radius where the equations broke, physics should break too. A surface. An edge. A place where matter arrived and something happened to it. Compression, heat, resistance, an event you could point at and measure. He changed coordinates. The infinity vanished. There was nothing there at all. Lemaitre published the result in 1933 in Annales de la Société Scientifique de Bruxelles, and it was largely ignored for 25 years until David Finkelstein rediscovered it in his 1958 paper in Physical Review, showing the surface is a one-way membrane rather than a wall. The curvature at that radius is given by the Kretschmann scalar, which falls off as 1 over r to the 6th power. For Sagittarius A, the 4.3 million solar mass hole at our galactic center, the tidal stretch across a 2-meter body at the crossing point is roughly 1/10,000th of Earth's gravity. Physicists spent decades hunting for a local signal anyway. Measure curvature, finite, and smaller than the tidal force you feel standing on Earth. Look for a change in the laws of physics, the equivalence principle forbids it, free fall is free fall everywhere. Look for radiation. Unruh radiation appears only if you fire engines, and firing engines is what a free-falling observer does not do. The membrane paradigm of Thorne, Price, and MacDonald in 1986 gave the horizon electrical resistance and viscosity, and all of it exists only in the accounting of observers who stay outside. Which leaves you with this. The most consequential boundary in physics is unmarked. No alarm, no jolt, no shudder in the chest, no moment of knowing. Your watch keeps time. Your heart keeps beating. The universe behind you looks, for the moment, entirely normal, and the density required to build one of these horizons falls as the square of the mass, which means a large enough horizon can enclose air, rock, stars, and people at ordinary density. So how, exactly, would you check? The answer to what happens next depends entirely on how big the thing is. Number 11. The death that depends on size. In 1975, Jack Hills at the University of Michigan was working on a purely astrophysical accounting problem. What powers quasars and Seyfert galaxies? His method was to calculate what happens to ordinary stars that wander too close to a massive central object, because shredded stars make a plausible fuel supply. The expectation was uniform destruction. Gravity near a black hole is extreme, so anything approaching should be pulled apart, the near side accelerated harder than the far side until the object is drawn into a thread. Hawking would later popularize the word spaghettification. Hills found the destruction has an upper mass limit. Above a certain black hole mass, the star is not torn apart at all. It is swallowed whole. The result appeared in Nature in 1975, and the threshold is now called the Hills mass, around 100 million solar masses for a Sun-like star. The reason is that tidal force at the horizon scales as 1 over the mass squared. For a 10 solar mass black hole, the stretch across a 2-meter body at the horizon is about 200 million meters per second squared, roughly 20 million times Earth's gravity. For Sagittarius A, at the same location, it is about 1,000th of a meter per second squared. Every attempt to rescue the intuition has failed. Reinforce the object, the difference in gravitational pull does not care about material strength past a threshold, and no material reaches it. Fall faster, the tidal field at the horizon is fixed by mass alone. Approach along a different trajectory, rotation changes the geometry but not the scaling. Pick a smaller hole to survive longer outside. Smaller holes are precisely the ones that destroy you before you arrive. The conclusion inverts every instinct you have about danger. A black hole the mass of a city block would kill you at a distance of thousands of kilometers. A black hole, the mass of a galaxy's core, lets you cross the point of no return with your body intact, your eyes open, your thoughts continuing normally. The larger the thing that has taken you, the longer you remain awake inside it. Which one would you choose? Assuming you keep your eyes open, the first thing you notice is the sky. Number 10. The sky that closes behind you. In 1978, Jean-Pierre Luminet was a young researcher at Paris Meudon Observatory with access to an IBM 7040 and a stack of punch cards. He was not making art. He was computing photon trajectories to work out how a black hole would appear if anyone ever built a telescope good enough, a technical exercise in ray tracing, output plotted by hand in India ink because the machine could not draw. The naive expectation is a black disk against ordinary stars, with the disk growing as you approach, the way any object grows as you close on it. The image that emerged was nothing like that. Light from behind the hole was bent around it and delivered to the front. The sky was folded. Luminet published in Astronomy and Astrophysics in 1979. The physics behind the distortion is relativistic aberration combined with gravitational lensing, and the numbers are exact. An observer falling from rest at a great distance sees the dark region subtend an angular radius of 90 degrees at the moment of crossing. Half your sky is black. The entire remaining universe, every galaxy, every star, the cosmic microwave background, is compressed into the other half, blue-shifted and brightened toward the rim. Astronomers tried for years to describe this more simply, and each simplification broke. Say the hole looks bigger as you approach, it does not. Aberration from your own infall pushes it back. Say you see the sky behind you. You see infinitely many copies of it, stacked in rings near the edge. Say the view goes dark. It does the opposite. The compressed light concentrates. Say the effect is an illusion of the coordinates. Andrew Hamilton and Gavin Polhemus rendered it in full general relativity in New Journal of Physics in 2010. And the geometry holds. Everything you have ever seen, everyone you have known, every photon that ever left Earth heading your way, arriving simultaneously in a shrinking bright circle overhead. And then the circle keeps shrinking. What is the last thing in that circle? That circle is where the most durable myth in physics lives. Number 9. The end of the universe you never see. The claim is everywhere. As you fall in, you watch the outside universe speed up. And in your final moments, you witness the entire future history of everything. It came from a real calculation. Schwarzschild's time coordinate diverges at the horizon, and generations of writers read that divergence as a statement about experience. If it were true, the infalling observer would receive an unbounded stream of light, every event in the external universe, all of cosmic history. Delivered before impact. The past light cone says otherwise. You cross in finite proper time, and you receive only the signals that were already on their way. The distinction was made rigorous by David Finkelstein in 1958, and formalized in the coordinate systems of Paul Pineleff in 1921 and Alvar Gullstrand in 1922, in which nothing dramatic happens to time at the crossing at all. Hamilton and Polhemus computed the actual view in 2010. The external universe visibly speeds up only modestly, and what arrives at the singularity is a finite slice of outside history, not an infinite one. Every attempt to save the myth collapses under scrutiny. Point to the diverging Schwarzschild time that describes an observer who hovers, burning fuel, never falling. Point to the infinitely redshifted images from outside. Those belong to the outside observer's picture of you, not yours of them. Argue that the fall takes infinite time. It does not. It takes microseconds. Argue that light piles up at the horizon. It does not. There is no accumulation surface. You do not get a final vision. You do not get to see how it ends, whether your species survives, whether anyone ever came looking. You get the news that was already in transit, and then you get the rest. The universe you fall out of continues without you, and you are given no report. Was there anything left to see? That absence of a report has a geometric cause, and the cause is stranger than the effect. Number 8. The singularity that is a date. In 1964, Roger Penrose was walking to his office at Birkbeck College in London with a colleague, discussing something unrelated, and stopped talking mid-conversation while crossing a side street. He was working on the general question of whether collapse always produces a singularity, or whether real, messy, asymmetric stars would miss the center and bounce. The prevailing assumption was that the singularity was an artifact of perfect symmetry. Real stars are lumpy and spinning. Lumpy spinning matter should swirl past the center, not converge on it. Penrose realized that once a surface exists from which light rays converge inward in every direction, the collapse cannot be undone by any amount of asymmetry. He published it in Physical Review Letters in 1965 in 3 pages, introducing the trapped surface, and it earned the Nobel Prize in Physics 55 years later. The geometry underneath it is what makes the inside so difficult to describe. Below the horizon, the radial coordinate and the time coordinate exchange roles. Decreasing radius becomes the future direction. Every intuitive escape route dies here. Fire engines outward, you are attempting to accelerate into yesterday. Orbit instead of falling, there are no stable orbits, the geometry has no static directions left. Aim sideways, every direction available to you has decreasing radius in its future. Build a stronger ship, no engine addresses the problem, because the problem is not force. The singularity is not a location in front of you. It is an appointment. You cannot point at it, avoid it, or steer around it for the same reason you cannot steer around next Tuesday. Everyone reading this is already moving toward their own future at exactly 1 second per second. Inside, that is all the singularity is. So what precisely is the difference? There is one lever left, and pulling it makes things worse. Number 7. The rocket that kills you faster. In 2007, Geraint Lewis and Juliana Kwan at the University of Sydney were preparing teaching material on relativity. A standard student question kept coming up. If you fell into a black hole, what should you do to survive as long as possible? The textbooks did not have a clean answer, so they worked it out. The intuitive answer is obvious and universal. Fight, fire your engines away from the center, slow the descent, buy time. They found that firing your engines shortens your life. Every deviation from freefall reduces the time you have left. Their paper, No Way Back, Maximizing Survival Time Below the Schwarzschild Event Horizon, appeared in publications of the Astronomical Society of Australia in 2007. The reason is that proper time along a path in curved spacetime behaves like a maximum, not a minimum. The freefall trajectory is the one that ages the most. An acceleration in any direction cuts the accumulated time. Each rescue strategy fails on the same principle. Full thrust outward, maximum reduction in proper time, you arrive soonest. Partial thrust, proportionally less time. Thrust sideways for an orbit, still acceleration, still shorter. Brief burns to coast. Lewis and Kwan showed the optimal profile is to fall from the horizon with the engines cold, and if you entered under power, to shut them off immediately. The single most human response available to you, struggle, resist, fight for 1 more second, is the response that costs you the seconds you have. To live longest inside a black hole, you must lie perfectly still and do nothing at all. You would have to decide, in advance, to accept it. Could you? And the exact number of seconds you are giving up is not a mystery. Number 6. The formula for your remaining life. The calculation was not motivated by mortality. Charles Missner, Kip Thorne, and John Wheeler were writing the textbook Gravitation, published in 1973, and needed a worked example of proper time along time-like geodesics that students could actually compute. Radial infall inside a Schwarzschild horizon was the cleanest case available. For most physical questions, the answer depends on initial conditions, your speed, your angle, where you started, how you arrived. It does not. The maximum possible proper time from horizon to singularity depends on one quantity, the mass. The result is pi times g times m divided by c cubed. For one solar mass, that is roughly 15 microseconds. For a 10 solar mass hole of the kind LIGO detects merging, about 155 millionths of a second. For Sagittarius A at 4.3 million solar masses, 66 seconds. For M87, the 6.5 billion solar mass hole imaged by the Event Horizon Telescope in 2019, roughly 28 hours. Attempts to extend it all fail. Enter at high speed, worse, you have less proper time than free fall from rest. Enter tangentially, angular momentum reduces it. Find a rotating hole and thread the inner region, the geometry changes but the ceiling remains set by mass. Wait inside, there is no waiting. Waiting is acceleration. You can calculate, from a single number, the exact duration of the rest of your life. 28 hours in M87 is enough time to sleep, eat, think it through, and say something to whoever came with you. 66 seconds in our own galaxy's center is enough to notice. The universe has never given anyone else an exact figure. Would you want it? All of that assumes you crossed a horizon at all, and in 2012, 4 physicists found a reason to doubt it. Number 5. The wall that should not be there. Ahmed Almheri was a graduate student at UC Santa Barbara. Given what looked like a safe project, check the internal consistency of black hole complementarity, the framework Leonard Susskind, Laris Thorlacius, and John Uglum proposed in 1993 to reconcile information conservation with the smooth horizon. Donald Marfolf, Joseph Polchinski, and James Sully expected the check to confirm it. Complementarity rests on 3 assumptions: unitarity, so information escapes, standard physics outside the horizon, and nothing unusual at the crossing itself, exactly as described at the start of this list. The 3 cannot all be true. They discovered the assumptions are mutually inconsistent, and something has to be sacrificed. The paper: black holes, complementarity, or firewalls, was posted in July 2012 and published in the Journal of High Energy Physics in 2013. The argument turns on the monogamy of entanglement after the Page time, Don Page, Physical Review Letters, 1993, the point at which half the black hole's entropy has been radiated. An emitted quantum must be maximally entangled with 2 different systems at once, which quantum mechanics forbids. Break the entanglement with the interior partner, and the horizon becomes a shell of Planck energy radiation. The escape attempts have been serious, and none has closed the case. ER equals EPER, proposed by Juan Maldacena and Susskind in 2013, geometrically beautiful, still contested. State dependence, from Kyriakos Papadodimas and Suvrat Raju, buys consistency by making the interior observer dependent. Simply denying unitarity abandons quantum mechanics. Denying the smooth horizon, that is the firewall itself. If the firewall exists, everything described in this video's first 2 minutes is wrong. There is no gentle crossing, you are incinerated at the boundary, and no signal warns you. 14 years later, no one has resolved it. So which of your 3 most trusted physical principles are you willing to give up? Assume you survive the crossing anyway. The inside is not empty. Number 4. The wall made of everything before you. In 1989, Eric Poisson and Werner Israel at the University of Alberta were studying a stability question that seemed technical. Charged and rotating black holes have a second horizon inside the first, the Kachi horizon, and Roger Penrose had noted in 1968 that light falling onto it arrives infinitely blue-shifted. Poisson and Israel wanted to know how the geometry responds. The clean solutions predict that you pass the inner horizon and enter a region where the equations lose predictive power, but nothing physically violent happens. The mass function diverges. Everything that ever fell in is compressed against that surface, and its gravitational effect grows without bound. They published inner horizon instability and mass inflation in black holes in Physical Review Letters in 1989, and developed it in Physical Review D in 1990. The effect is exponential, with an E-folding time set by the surface gravity of the inner horizon, and the curvature can exceed the Planck scale within a fraction of a second of local time. The subsequent history is a sequence of narrowing hopes. Argue that it is an artifact of the charged non-rotating model, Mihalis Daframos and Jonathan Luke extended the analysis to rotating Kerr geometry, and the instability survives. Argue that infinite curvature means instant destruction. Amos Ori showed in Physical Review Letters in 1991 that the tidal distortion integrates to a finite value, so an observer might pass through deformed but intact. Argue that quantum gravity smooths it, no one can compute that. Argue that real black holes never form inner horizons, every rotating black hole has one. The interior is not a void. It is a compressed archive of every object that ever fell in, and you are falling toward all of them at once. Every star, every atom, everything that arrived before you, waiting at a surface. What is it like to arrive there last? There is one proposal that removes the interior entirely. Number 3. The inside that isn't there. Oleg Lunin and Samir Mathur at Ohio State University were doing string theory bookkeeping. The task was counting microstates for a specific configuration, the two-charge D1-D5 system, to check whether string theory reproduces the Bekenstein-Hawking entropy. Pure accounting, in a controlled setting. A black hole with entropy should have its microstates hidden behind a horizon, all of them identical from outside, all differences buried at a central singularity. The microstates had no horizon and no singularity. Each one ended in a tangled surface sitting exactly where the horizon should have been. Lunin and Mathur published in Nuclear Physics B in 2002, and Mathur laid out the general proposal, now called the fuzzball, in Fortschritt der Physik in 2005. The surface sits at the Schwarzschild radius to within a fraction of a Planck length, and the number of distinct configurations reproduces the entropy formula exactly, the exponential of 1/4 of the horizon area in Planck units. The objections have narrowed rather than won. Argue that the construction only works for supersymmetric, extremal, unrealistic holes. The extension to astrophysical black holes remains incomplete, and that is the strongest criticism standing. Argue that it contradicts the equivalence principle. Mathur's fuzzball complementarity claims infalling matter of high enough energy still experiences an approximately smooth interior. Argue it is untestable. Gravitational wave echoes after merger would be the signature. And searches in LIGO data have so far found nothing conclusive. If Mathur is right, there is no inside. You do not fall through anything. You reach the surface and you stop, spread across it, converted into vibrating strings on a shell two-dimensional in every practical sense. No crossing, no interior, no fall. Just a surface. And then you are part of it. Would that count as arriving? Whichever picture is correct, something about you does get out. Number 2. The pattern that survives you. Jeff Pennington was a graduate student at Stanford in 2019 working on entanglement wedges and holographic duality, a technical tool for figuring out which part of a bulk spacetime a boundary region can describe. Independently, Ahmed Almheri, Netta Engelhardt, Marfulf and Henry Maxfield were pursuing the same machinery at Princeton and MIT. Hawking's 1974 calculation says the radiation leaving a black hole is thermal, featureless, structureless, carrying no record of what fell in. Entropy rises forever, and the information is destroyed. Both groups found extra regions contributing to the entropy calculation. Disconnected pieces of the black hole interior, now called islands. Include them, and the entropy turns over. The turnover reproduces the page curve, the shape Don Page derived in 1993 for any process that conserves information. Entanglement entropy rises until roughly half the black hole has evaporated, then falls back to zero. Pennington's paper and the Almheri-Engelhardt-Marolf-Maxfield paper both appeared in the Journal of High Energy Physics in 2020, and the result now has multiple independent derivations. Every reading that makes this comforting fails. Read it as recoverable information. Patrick Hayden and John Preskill showed in 2007 that retrieval requires the full radiation record and computation on a scale no physical apparatus approaches. Read it as your body reassembling. It does not. The correlations are scrambled beyond any practical inversion. Read it as evidence of continuity of experience. Nothing in the calculation touches experience. Read it as an afterlife. The equations describe correlations in outgoing quanta. Nothing more. Here is the precise statement, and it deserves to be stated precisely. Your pattern is conserved. Every atom, every memory, every arrangement that made you specific is written into the outgoing radiation and is never erased from the universe. And you are gone. The record survives, the person does not. Which of those two facts is the one that matters? Which leaves the final question, and it has two answers that contradict each other and are both correct. Number 1. The two answers that are both true. On the 1st of September 1939, the day Germany invaded Poland, Physical Review published a paper by J. Robert Oppenheimer and his student Hartland Snyder. They were not speculating about exotic objects. They were following up on the maximum mass of a neutron star and asking the mundane question of what happens to a star too heavy to hold itself up. The expectation was that something would intervene. Pressure, rotation, radiation, nuclear forces, some mechanism halts the collapse. Nothing halts it. And the paper contains a second finding, stated almost in passing: the collapse looks completely different depending on who is watching. Oppenheimer and Snyder showed that in the frame of the collapsing matter, the process ends in finite time. While for a distant observer the star's surface approaches the critical radius asymptotically and never reaches it. For a 10 solar mass black hole, your proper time from horizon to singularity is at most 155 microseconds. For the universe outside, that crossing never completes. There is no reconciliation, and physicists stop looking for one. Declare the infalling frame real and the outside view an illusion. The outside view is what every telescope measures. Declare the outside view real and the fall an illusion. The fall is what the falling observer's clock records. Split the difference. There is no coordinate system that makes both descriptions into one description. Complementarity was the attempt to hold both, and item 5 is what happened to complementarity. Both are true. From your side, it took less time than a nerve impulse. From every other perspective in the universe, you are still falling, and always will be, at a boundary that gets dimmer by a factor of roughly every 10,000th of a second until no instrument can find you. Frozen forever, and finished instantly. Which of those two is you? 12 entries, and not one of them comes from the frontier of physics. Every anomaly on this list, the unmarked crossing, the traded coordinates, the firewall, the island, comes from the center of our most tested theories. General relativity and quantum mechanics have each passed every experiment ever devised for them. And where they meet, they describe your death in two mutually exclusive ways and refuse to choose. The universe is not confused about what happens to you inside a black hole. We are. And the same equations that fail here are running right now, quietly and without contradiction, on the ordinary matter of your body. If you want to see more videos like this, click the video on screen now.